Look at a galaxy spinning 10 billion light-years away, shining with a light it has no right to have this early in time. James Webb's Space Telescope was built to look back toward the birth of everything, and it found something that breaks every rule we know. Massive galaxies were already glowing bright before the universe turned 500 million years old. One giant galaxy refuses to spin at all. Strange little red dots might be newborn black holes hiding inside a cloak of dust. If a real cosmic mystery grabs you, hit subscribe now, because tonight we travel farther back than light has ever carried us. Brace yourself, we begin. 4 instruments and 18 gold hexagon mirrors waited in the frozen dark, 1 million miles from home. The James Webb Space Telescope hung at a point in space called the second Lagrange point, far past the orbit of the Moon, where the pull of the Earth and the pull of the Sun balance out just enough to let a spacecraft sit still. Its instruments were chilled to nearly the temperature of deep space itself, colder than anywhere on Earth, so faint heat from its own machinery would not drown out the whispers it came to hear. Those whispers were not sound. They were infrared light, a kind of light too red for human eyes to see, carried across billions of years by photons stretched thin by the expansion of the universe. Picture a rubber band with a drawing on it. Stretch that rubber band, and the drawing stretches too. Light behaves the same way. As the universe expands, the light travelling through it stretches longer and longer, sliding from visible colours into deep red, then past red into infrared. The farther the light has travelled, the more it has stretched. A telescope built to catch infrared light is really a telescope built to catch the oldest light there is. The 6.5-metre mirror, launched past the Moon, existed for one job: to look back in time. Light takes time to cross space, so a galaxy 10 billion light-years away is not being seen as it is today. It is being seen as it was 10 billion years ago, frozen in a beam of light still crossing the gap between then and now. The farther Webb looked, the further back in time it travelled, all the way toward the first few 100 million years after the universe began. Before Webb, the Hubble Space Telescope had already pushed close to that edge, catching blurry hints of galaxies near the dawn of time. Hubble was built to see visible light, the same kind human eyes use, and the oldest galaxies had stretched their light too far into infrared for Hubble to catch clearly. Webb was different, tuned to see through cosmic dust and across almost the entire age of the universe. Scientists expected Webb to confirm what they already believed about the early universe. Small, faint, messy galaxies, still learning how to build themselves. A slow, patient story of gas clumping together over hundreds of millions of years. Nobody expected the first images to argue back. Within its first few months of operation, Webb sent back pictures that made astronomers stop and stare, question their screens, and rerun their calculations. Somewhere in that ancient starlight sat something that should not have been possible so early in cosmic history. And the first clue came from a patch of sky nobody thought was interesting at all. Near the Big Dipper, in a stretch of sky Hubble had already photographed back in the 1990s, sat a patch of space astronomers considered almost boring. No bright galaxies, no dramatic nebulae, just a quiet field of faint smudges stacked behind each other in the dark. It was exactly the kind of empty-looking region astronomers use to search for the faintest, farthest objects, because nothing nearby gets in the way. In the summer of 2022, Webb pointed its mirror at that patch as part of a survey project. Teams of astronomers around the world began combing through the resulting images, pixel by pixel, hunting for anything unusual hiding among the thousands of faint dots. Erica Nelson, an astrophysicist at the University of Colorado Boulder, was studying a small section of one image when something stopped her cold. A few fuzzy dots of light sat there, glowing far too brightly for objects that should have been almost invisible at that distance. She checked the numbers again. She checked the calibration. The dots stayed just as bright, just as strange. Most distant galaxies show up as faint, barely there smudges, stretched thin by billions of years of travel. These dots looked packed tightly together and lit on fire, glowing with far more light than a young, small galaxy should be able to produce at that age. Nelson brought her discovery to colleagues, including astronomer Ivo Labbe in Australia. An informal team began to form, spread across 4 countries, all chasing the same strange signal. They started out simply testing the telescope, learning how to use this powerful new instrument, mapping the early universe the way scientists expected it to look. Faint, small, slowly assembling itself piece by piece, the way galaxy formation models had predicted for decades. Instead, tucked inside a patch of sky nobody had bothered to study closely before, sat something that did not fit any of those predictions. The team kept digging. What started as one strange dot near the Big Dipper turned into a careful hunt through Webb's images for more of the same, and they found them. Not one impossible object, but a small cluster of candidates, each one glowing in that same telltale way, each one hinting at something massive hiding at the edge of time itself. Whatever these objects were, they were about to challenge everything astronomers thought they understood about how fast a galaxy could grow. By the time the team finished combing through the data, 6 separate candidate galaxies sat on their list, each one glowing with the same suspicious brightness Nelson had first spotted near the Big Dipper. 6 tiny points of light, buried among thousands of ordinary galaxies, all sharing one trait that made astronomers uneasy. They looked far too developed for how early they had appeared in the history of the universe. Based on how much their light had stretched during its long journey, the team calculated that these galaxies existed somewhere between 500 million and 700 million years after the Big Bang. That sounds like an enormous stretch of time, and by human standards it is. But measured against the full 13.8 billion year age of the universe, 500 million years is closer to the first few weeks of a newborn's life. Nobody expects a newborn to already be walking, talking, and running errands. Yet here were 6 galaxies, apparently doing exactly that. According to the standard model of cosmology, the model most astronomers had trusted for decades, galaxies are supposed to build themselves slowly. Clouds of gas drift together under gravity, clump into small pockets of stars, then merge with neighbouring pockets over hundreds of millions, even billions, of years. Growth is gradual. Galaxies start small and messy, and only later become large and organised. That process should take time, plenty of it. These 6 candidates seem to be skipping the line. Whatever process built them had somehow compressed an enormous amount of growth into an incredibly short window, right at the very start of cosmic history, back when the universe itself was still cooling down from its explosive birth. The team could not simply announce a discovery this strange without being certain. So they ran the numbers again, checked for contamination from foreground objects, and looked for any simpler explanation. Nothing obvious came up. The strange brightness held steady, the strange timing held steady, and one uncomfortable possibility kept surfacing. These objects might really be what they appeared to be, galaxies that grew far too fast, far too early, for any current theory to fully explain. Word of the discovery began spreading fast through the astronomy community, long before the official announcement. Astronomers who had spent entire careers building and refining models of galaxy formation found themselves staring at data that simply did not fit. If even one of these 6 candidates held up under closer scrutiny, it would mean rewriting a piece of the story of how the universe built its first great structures, and one candidate in particular stood out from the rest, not just for existing too early, but for how enormous it appeared to be once the team worked out its size. One candidate on that list of 6 stopped the team in its tracks. Based on its brightness and the light it gave off, this single galaxy appeared to contain almost as many stars as the modern-day Milky Way, a galaxy that took over 13 billion years to build. The Milky Way holds somewhere around 100 billion stars spread across a disk roughly 100,000 light-years wide. This newly spotted galaxy seemed to be carrying a similar stellar population, only it had done so within the first 700 million years of cosmic history. Here is where the numbers get stranger still. This galaxy was not spread out across a huge area. It was compact, packed into a region roughly 30 times smaller in size. Imagine taking every person living in a sprawling city and squeezing them into a single office building. Everyone's still there. Everyone's still breathing, just packed impossibly close together. That is roughly the kind of density astronomers were looking at, except with stars instead of people, and a whole galaxy instead of a building. Building that many stars normally takes an enormous amount of time. Stars form from clouds of gas collapsing under their own gravity, a slow process that unfolds over millions of years per generation. To match the Milky Way's star count this early, this galaxy would have needed to convert gas into stars at a blistering pace, far faster than astronomers believed was physically possible for something so young. There is another wrinkle buried in the light itself. The colour and brightness of starlight can reveal not just how many stars a galaxy holds, but roughly how old those stars are. Older stars tend to burn cooler and redder. When the team studied this galaxy's light more closely, some of it hinted at stars that had already been burning for a while. A galaxy old enough to already contain aging stars, sitting at a point in time when the universe itself was barely out of its infancy, made the puzzle even harder to explain. Every angle the team checked led back to the same uncomfortable conclusion. Either something was wrong with their measurements, or a galaxy this size had somehow assembled itself in a fraction of the time astronomers thought was required. They rechecked their tools, cross-referenced their data, and kept arriving at the same strange answer. If the numbers held up, this single compact galaxy was a direct challenge to decades of careful modelling about how galaxies are born and how quickly stars can form inside them. The question stopped being whether such a galaxy existed. The question became how nature had managed to build one so quickly, and what that meant for everything astronomers thought they understood about the beginning of everything. To understand why a galaxy like that broke so many rules, it helps to understand the rules themselves. For decades, astronomers have relied on a framework built from the best available data on how the universe expanded, cooled, and organised itself over time. According to that model, the very early universe was a smooth, dark, nearly featureless soup of hydrogen and helium gas, laced with invisible dark matter. For the first few 100 million years, nothing shone at all. Astronomers call this stretch of time the Cosmic Dark Ages, a period with no stars, no galaxies, just gas slowly drifting and clumping under the pull of gravity, guided by unseen scaffolding built from dark matter. Eventually, in pockets where gas gathered densely enough, gravity won out and the first stars ignited, ending the Cosmic Dark Ages and beginning what astronomers call Cosmic Dawn. Those first stars were scattered and chaotic. Slowly, gravity pulled these scattered star clusters together into small, messy proto-galaxies. Those small galaxies then merged with their neighbours, again and again, growing larger with each collision, the same way small streams merge into rivers and rivers merge into a single wide delta. This slow, step-by-step growth process is supposed to take a long time. Building something the size of the Milky Way, under standard assumptions, should require billions of years of mergers and star formation, not hundreds of millions. A galaxy needs enough generations of stars, enough collisions with neighbouring gas clouds, enough raw material converted into stellar light to reach that kind of scale. The 6 candidate galaxies Webb had found were essentially skipping most of those steps. They appeared fully assembled, bright, and in at least one case as massive as a modern galaxy, while the universe itself was still in the earlier stage of cosmic dawn. It was the equivalent of watching a sapling planted this morning, already standing as a full-grown oak tree by lunchtime. Astronomers do have some wiggle room in their models. Star formation rates can vary, gas can collapse faster under certain conditions, and dark matter halos of different masses can pull material together at different speeds, but the gap between prediction and observation here was not small. Some early calculations suggested these galaxies contained far more mass in stars than the standard model allowed for, given how little time had passed since the Big Bang. That gap is exactly what makes a discovery dangerous to a scientific model in the best possible way. A small disagreement gets explained away with better data. A disagreement this large forces scientists to ask a harder question. Is something fundamentally missing from the story science has been telling about how the first galaxies were built? Faced with a gap that large, the scientists behind the discovery did not reach for calm, careful language. Erica Nelson later described her reaction to the findings in blunt terms, admitting the results felt almost absurd. The early universe was not supposed to be capable of organising itself this quickly. These galaxies should not have had the time required to form. Word of the discovery spread through the astronomy community with an informal nickname attached: universe breakers. Nobody meant it as an official scientific term. It was shorthand, the kind of phrase researchers use among themselves when a result feels less like a small correction and more like a direct challenge to an entire framework. The team published their findings in February of 2023 in the scientific journal Nature, a publication reserved for discoveries considered significant enough to reshape a field. They were careful to note that these were candidate galaxies, promising but not yet fully confirmed, since Webb's earliest images alone could not settle every detail about their exact distance and mass. Confirming an object this far away with total certainty usually requires spreading the light out like a rainbow, measuring precise chemical fingerprints and an exact distance. Even with that uncertainty attached, the implications rippled outward fast. If even one or two of these 6 candidates turned out to be exactly what they appeared to be, astronomers would need to rethink core assumptions about star formation efficiency, about how quickly gas can collapse into stars, and about how much mass a single galaxy could plausibly gather within the first 700 million years of cosmic history. Some scientists urged caution, pointing out that early distance estimates for extremely faint distant objects can carry real uncertainty, and that a small number of these candidates could eventually turn out to be closer and therefore less extreme, once studied more carefully. That caution was reasonable. Extraordinary claims in astronomy always deserve extra scrutiny. Even skeptical astronomers had to admit that something in the early data pointed toward galaxies growing faster and bigger than expected, even if the most extreme individual cases eventually got revised. The pattern itself was becoming difficult to dismiss. These 6 galaxies from that one patch of sky near the Big Dipper turned out to be far from the only surprise Webb had waiting. As astronomers turned the telescope toward other regions of the sky, an entirely different kind of unexpected result was quietly building, this time involving not the size of early galaxies but their shape. Galaxies come in different shapes, and one of the most recognizable is the disk, a flat rotating structure with graceful spiral arms winding outward from a dense central bulge, the exact shape of our own Milky Way. Disk galaxies look calm and orderly, built from gas and stars settling into a smooth, spinning pattern over the long stretches of time, the same way pizza dough spreads into a flat circle when a chef spins it in the air. For decades, astronomers assumed disk galaxies like this were rare in the early universe, and for good reason. Back when the universe was young, galaxies were smaller, packed closer together, and colliding constantly. Every merger between 2 galaxies tends to stir things up violently, disrupting delicate structures like spiral arms, the same way stirring a swirled milkshake ruins its pattern. A fragile, orderly disk shape was expected to be the last thing standing after that kind of chaos, not the first. So when a team of astronomers used Webb to look deep into that same violent early era, they expected to find twisted, irregular galaxies or clumpy blobs still fighting their way toward any organized shape at all. Instead, they found something else entirely. Peering across roughly 10 billion years into the past, the team studied thousands of galaxies captured in Webb's images. They kept spotting galaxy after galaxy with a familiar shape, warped vinyl records with delicate spiral arms, quiet disks spinning peacefully in a period when astronomers had assumed peace should have been almost impossible to find. They showed up again and again, in image after image, existing during exactly the period when dwarf galaxies were supposedly swarming and colliding constantly, an era once considered far too rough for anything this fragile to survive intact. The discovery landed as yet another crack in the picture astronomers had built of the early universe. If violent mergers really dominated cosmic history the way models predicted, disk galaxies should have been a rare fluke this far back in time, quickly torn apart before settling into anything so neatly organized. Instead, Webb kept finding them, calm and structured, as if the early universe had been far gentler, or at least far more capable of quick recovery than anyone had given it credit for. Astronomers studying these results were left with an uncomfortable but familiar feeling by this point. Another piece of the standard story about the early universe was not lining up with what the telescope was actually showing them. and once the team counted up exactly how many of these disk galaxies they had found, the scale of the disagreement became impossible to ignore. Counting galaxies precisely is slow, careful work. The team behind this disk galaxy survey did not rely on a handful of striking images. They built a large methodical catalogue, studying thousands of galaxies across a wide stretch of cosmic history, from roughly 9 billion years ago, all the way back toward 13 billion years ago, right at the edge of what Webb can currently detect. Out of the galaxies included in their final analysis, the team identified nearly 4,000 total, and of those, well over 1,600 displayed the telltale spiral disk shape. That ratio stunned researchers who had built their careers on the older assumption that these structures should be rare during such a turbulent period of cosmic history. To understand why that number mattered so much, picture flipping through nearly 4,000 snapshots taken across 10 billion years of cosmic time, expecting most of them to show twisted, disrupted shapes torn apart by constant collisions. Instead, more than 4 out of every 10 snapshots showed a calm, spinning disk, quietly forming stars, largely untouched by the chaos astronomers had assumed would dominate. The pattern held up across the entire span the team studied, stretching back through billions of years, right through the era when galaxy mergers were supposed to be at their most violent and frequent. If disk galaxies really were this common, this early, then something about the standard picture of galactic chaos needed serious reconsideration. Researchers involved in the study pointed out that this finding fits into a larger, growing pattern. Webb kept turning up galaxies that appeared calmer, more organised, and more mature than anyone expected, whether astronomers were measuring total mass, star count, internal structure, or overall shape. Some scientists suggested that older telescopes, particularly Hubble, simply had not been sensitive enough to detect these calm disk shapes clearly at such extreme distances, meaning the disks may have been there all along, just hidden from view until a more powerful instrument came looking. That explanation offered some comfort, suggesting astronomers had simply been unable to see this pattern clearly enough before now. But even that explanation carried an unsettling edge. If Hubble had been blind to a pattern this widespread, it raised an uncomfortable question about how many other assumptions built from Hubble's limited data might also need revisiting. And the scale of that disagreement, roughly 10 times more disk galaxies than predicted, was about to become the next number that stopped astronomers cold. 10 times. That was the gap between what models predicted and what Webb actually found. Astronomers running computer simulations of galaxy formation had built detailed predictions for how many disk-shaped galaxies should exist at different points in cosmic history, based on everything known about gravity, gas physics, and the frequency of galaxy mergers in the young universe. Webb's actual count of disk galaxies came in roughly 10 times higher than those simulations expected. To put that gap in perspective, imagine flipping a coin, expecting it to land on heads once out of every 10 flips, based on careful calculations. Instead, it lands on heads every single time. A gap that size does not usually point to a small rounding error hiding somewhere in the math. It points to something the underlying model is missing entirely. For astronomers, this meant reconsidering a basic assumption baked into decades of galaxy formation research: that the early universe was dominated by chaos. Galaxy mergers do happen, and they clearly shaped much of cosmic history. But if calm, orderly disk galaxies were really this common, this early, then either those mergers were gentler than assumed, or galaxies were somehow able to rebuild their structure and settle back into an orderly disk shape, far faster than anyone had modelled. Either explanation carried real weight. A gentler early universe would mean astronomers had overestimated just how violent galactic collisions truly were during this period. A faster recovery process would mean galaxies possess some kind of resilience, an ability to reorganize themselves quickly after a disruptive event that current simulations simply were not capturing. Researchers were careful to note that this discovery, much like the earlier findings of unusually massive early galaxies, was not proof that the entire standard model of cosmology was broken. Science rarely gets overturned by a single result, however striking. Instead, discoveries like this act as pressure points, forcing scientists to test, refine, and sometimes rebuild pieces of a model that no longer matches what better instruments reveal. Still, the pattern emerging across multiple independent studies was becoming difficult to dismiss as coincidence. Galaxies too big, too soon. Galaxies too calm, too soon. Galaxies too organized, too soon. Each new result chipped away at the comfortable picture of a slow, chaotic, gradual build-up toward the organized universe seen today. Every one of these discoveries still relied on studying galaxies that existed somewhere between 500 million and roughly 4 billion years after the Big Bang. Astronomers were about to push even further back, chasing light from a time so early that some began to wonder whether they were approaching the very limit of what any telescope could ever hope to see. Somewhere in Webb's deepest images sat a target that would eventually claim the title of most distant galaxy ever confirmed, a record that keeps astronomers reaching further back in time with every passing year. Its name was not poetic, drawn from the survey that found it, JADES, short for a deep extragalactic survey program, and a string of numbers marking its measured distance. The team behind this survey had spent months combing through Webb's images, part of a larger effort using both the telescope's camera and its spectrograph to study galaxies from the earliest chapters of cosmic history. In October of 2023, and again in January of 2024, they turned their attention to a particularly faint, particularly red point of light buried deep in one of their survey fields. Based on how far its light had stretched, the team calculated that this galaxy existed just 290 million years after the Big Bang. To understand how early that truly is, remember that the universe as a whole is roughly 13.8 billion years old. 290 million years works out to barely 2% of that total age. If the entire history of the universe were compressed into a single calendar year, this galaxy would have existed sometime in the second week of January. Finding a galaxy this early is not simply a matter of luck or a striking picture. Confirming a distance this extreme requires spreading a galaxy's faint light out like a rainbow, studying exactly how far specific chemical fingerprints within that light have shifted toward red. The more that light has stretched, the further back in time the source must be. For an object this faint and this far, gathering enough of that stretched light to measure precisely takes patience and an enormous amount of telescope time. The team knew they might be looking at something record-breaking, but they needed to be certain before making any announcement. A distance this extreme, if confirmed, would push the boundary of observable galaxies back further than almost anyone expected Webb to reach this early in its mission. It would mean catching light from a galaxy that existed while the universe itself was still assembling its very first generation of stars and structures. So the team pointed Webb directly at this faint red target and prepared for one of the longest, most careful observations of the entire survey, determined to gather enough light to settle the question once and for all. Confirming a record like this takes more than a single glance. In January of 2024, the team pointed Webb's near-infrared spectrograph directly at their faint red target and left it staring for almost 10 straight hours. 10 hours might not sound dramatic on its own, but for a single, faint point of light sitting near the edge of the observable universe, every extra minute of observation matters enormously. Light from an object this distant arrives incredibly weak, scattered across billions of years of travel, stretched thin by the expansion of space itself. Gathering enough of that faint signal to measure it precisely means collecting photons patiently, hour after hour, slowly building up a clear enough picture to trust. While the observation ran, the team could do little but wait. 10 hours is a long commitment for a single target, especially on a telescope with an overflowing list of scientific priorities competing for its attention. When the data finally came back and the team began processing the resulting spectrum, the moment landed exactly the way astronomers hope every major discovery will land, unmistakable. The chemical fingerprints in the light lined up perfectly with a redshift value that shattered every previous record for confirmed galaxy distance. There was no ambiguity left to debate. Team members later described the moment as electrifying, the kind of result that makes years of painstaking survey work feel instantly worthwhile. This was a fully confirmed measurement, built from 10 hours of careful, direct observation, leaving little room for doubt, unlike the 6 massive galaxy candidates near the Big Dipper that still awaited additional confirmation. What made the moment even more striking was what the confirmed distance implied about the galaxy itself. An object this far away, this early in cosmic history, needed to be intrinsically very bright just to be detectable at all by Webb's instruments. Faint galaxies simply do not survive a journey this long and still register clearly enough to measure. Whatever this galaxy was, it had to be shining with real intensity, even while the universe itself was still in its earliest, rawest stage of formation. The confirmed number itself, once it emerged from the data, turned out to be even more extreme than the team had initially expected walking into the observation. And that single number was about to become one of the most talked about figures in modern astronomy. The number was 14.32. In astronomy, that number is called a redshift, and it measures exactly how much a distant object's light has stretched during its long journey across an expanding universe. Understanding redshift starts with something far more familiar: sound. Picture an ambulance racing past with its siren blaring. As it approaches, the sound waves compress together and the pitch sounds higher. As it speeds away, those same sound waves stretch out and the pitch drops lower. Light behaves in a similar way when the source is moving away, except instead of the pitch dropping, the colour shifts. Light waves stretch longer, sliding away from blue and green, through red, and eventually past red entirely into infrared. Now scale that idea up to the entire universe. Every point in space is moving apart from every other point, stretched by the ongoing expansion of the cosmos itself, not because galaxies are flying through space like rockets, but because space itself keeps growing larger everywhere at once. The farther away a galaxy sits, the more space lies between it and Earth, and the more that space has stretched during the time its light spent travelling toward us. More stretching means a higher redshift number. A redshift of 14.32 means the light from this galaxy has been stretched by an enormous factor during its journey. Wavelengths that started out somewhere in the visible or ultraviolet range arrived at Webb's instruments stretched far into the infrared. Exactly the kind of light Webb was built specifically to detect. No previous space telescope had the sensitivity to catch light stretched this extremely, and still measure it with enough precision to confirm a distance this exact. This single number shattered the previous confirmed distance record, a redshift of 13.2 that had stood for roughly 2 years before this new measurement, pushed the boundary even further back into the depths of cosmic history. For the scientists involved, a number this precise confirmed that Webb was capable of reliably detecting and measuring galaxies from a period of cosmic history previously considered nearly impossible to study directly. It opened a door toward an entire population of extremely early galaxies that earlier telescopes simply could not have found. Translating a redshift number into an actual amount of elapsed time requires careful mathematics involving the expansion rate of the universe. Once the team ran those calculations, the answer placed this galaxy at a point in cosmic history so early that it forced astronomers to reconsider, once again, exactly how quickly a galaxy could form, grow, and start shining this brightly. Run the math on a redshift of 14.32 and the answer lands somewhere close to 13.5 billion years ago. That is roughly how long this galaxy's light has been travelling before finally reaching Webb's mirror. Compared against the full 13.8 billion year age of the universe, this galaxy existed when everything was only about 2% as old as it is today. Picture the entire history of the universe stretched out along a single football field, end zone to end zone, with the Big Bang sitting at one goal line and today sitting at the other. A galaxy appearing 2% of the way across that field would sit barely 2 yards past the starting line, practically still standing in the end zone while the rest of cosmic history stretched out ahead of it, almost entirely unwritten. Despite existing at a moment this early, this galaxy registered as unmistakably bright in Webb's instruments, bright enough to gather a clear, detailed spectrum within that 10-hour observation. Team members involved in the discovery pointed out that this brightness carried real scientific weight. An object this far away needs genuine intrinsic luminosity just to remain detectable at all, since distance alone dims an object's apparent brightness dramatically. Measurements of the galaxy's physical size added another surprising detail. Despite forming so early, it already spanned roughly 1,600 light-years across. A real, structured object rather than a single tiny clump of newborn stars. For comparison, that is a meaningful fraction of the size of many nearby dwarf galaxies, built within a fraction of the time astronomers assumed such structures required. Researchers studying the galaxy's light found that most of its brightness appeared to come from genuine starlight, produced by a substantial population of young, hot stars, rather than emission from a growing black hole at its centre, a possibility astronomers always have to rule out carefully when studying unusually bright, compact objects this far away. That distinction mattered. It meant this really was a rapidly star-forming galaxy, building stars at an impressive pace. Taken together, the size, brightness, and confirmed distance painted a picture of intense, rapid galaxy formation, happening far earlier than most models expected to be possible. Team members noted that finding an object this luminous within such a small patch of sky suggested many more similarly bright, similarly early galaxies were likely waiting to be found across the rest of the observable sky. This record was never going to be the final word. Records like this rarely last long once a telescope proves capable of finding them. Before that discovery claimed its title, another galaxy briefly held the record for most distant confirmed object in the observable universe, confirmed back in October of 2022, one of Webb's very first major scientific results after beginning operations. At the time, that earlier confirmation represented a genuine milestone. Its measured redshift of 13.2 meant astronomers had confirmed a galaxy dating back roughly 13.4 billion years, existing when the universe was around 400 million years old. For a brand new telescope only recently arrived at its observation post, confirming a distance this extreme within its first year of operation felt like an enormous achievement. For nearly 2 years, that galaxy held its title as the earliest, most distant confirmed galaxy known to science. Astronomers studied it carefully during that period, using it as a benchmark for understanding just how early galaxy formation could realistically begin, and refining their techniques for finding similarly distant objects hidden elsewhere in Webb's deep survey images. Then, within months, the survey team pushed the boundary even further back, confirming the new record at redshift 14.32, corresponding to a galaxy existing just 290 million years after the Big Bang, roughly 100 million years earlier than its predecessor. 100 million years might sound like a small adjustment sitting next to numbers already measured in billions. But at this extreme edge of cosmic history, every additional 100 million years pushed backward matters enormously, since the earliest stages of galaxy and star formation were unfolding rapidly during this exact window of time. Finding a fully formed, brightly shining galaxy just 100 million years earlier than the previous record meant astronomers had to squeeze an already tight timeline for galaxy formation even tighter. This rapid turnover between record holders revealed something important about Webb's own capabilities. The telescope kept demonstrating that it could reliably detect and precisely confirm galaxies existing at increasingly extreme distances, one survey at a time. Each new record suggested the true limit was simply how much survey time and patient-searching astronomers had been able to dedicate so far. If a telescope keeps breaking its own distance records within a single survey program, spanning barely 2 years of operation, it raises an obvious question about what else might be hiding even further back, waiting patiently in the data for someone to notice. And elsewhere in Webb's growing catalogue of strange discoveries, an entirely different kind of puzzle was quietly taking shape, this one involving not distance but motion. Roughly 2 billion years after the Big Bang, in an era when the universe was still assembling its first generation of large galaxies, astronomers using Webb spotted something that immediately felt wrong. A massive galaxy, fully formed and impressively large for its age, appeared to have no rotation at all. Galaxies are not static objects sitting motionless in space. Most large galaxies spin, slowly rotating around their own centre, the same way a plate spins on a performer's fingertip. That spin is a direct fingerprint of how the galaxy formed. Gas clouds collapsing under gravity naturally carry some rotational motion inherited from the larger structure they condensed out of, the same way water naturally starts swirling as it drains from a bathtub. As that gas collapses further and organizes itself into a galaxy, the spin typically becomes more pronounced, similar to how a figure skater speeds up by pulling their arms in close to their body. Given that basic physics, astronomers expect young galaxies, especially massive ones still actively forming, to display clear rotational motion. Spin is one of the clearest signs of an organized, settled structure. Older, more evolved galaxies sometimes show reduced rotation after undergoing violent events, like a head-on collision with another galaxy that scrambles orderly motion into chaos. But a young galaxy showing essentially zero rotation breaks the expected pattern entirely. That is exactly what this galaxy displayed. Detailed measurements of how its gas and stars were moving revealed no meaningful large-scale rotation at all, a trait astronomers typically associate only with much older, already evolved systems, or systems disturbed by some kind of disruptive event long after their initial formation. Finding this trait in a galaxy still less than 2 billion years old immediately raised questions. Had something violent interrupted its formation early on, scrambling any rotational motion before it had a chance to properly establish itself? Had it formed through some unusual process that never generated significant rotation in the first place? Or did this discovery suggest astronomers were still missing something fundamental about how galaxies acquire their spin during the earlier stages of formation? None of the obvious explanations fit comfortably. This galaxy appeared massive enough and organized enough to suggest a fairly standard settled formation process, the kind that should naturally produce clear rotational motion. Yet the motion simply was not there, measured directly in Webb's data, difficult to dismiss as a simple error. Astronomers studying the result were left facing a genuinely open question, one without an easy answer yet available. And that open question fit directly into a much larger pattern, quietly building across nearly every major early galaxy Webb had studied so far. A young galaxy acting old challenges more than just one specific measurement. It challenges the entire timeline astronomers use to understand how galaxies mature over cosmic history. Under standard models, age and behavior are supposed to move together in predictable ways. Young galaxies should still be actively forming stars at a rapid pace, rich with gas, often somewhat disorganized in shape, and typically showing clear rotational motion inherited from their initial collapse. Older galaxies gradually settle down. Star formation slows as available gas gets used up. Structures become more stable over long stretches of time. In some cases, especially after violent mergers, rotation can slow or stop entirely, leaving behind a system where stars move in more random, scattered directions, rather than following one smooth, organized spin. Finding a galaxy under 2 billion years old that already displays this older, settled, non-rotating behavior scrambles that expected timeline. It is the equivalent of meeting someone who looks, walks and talks exactly like a retiree, only to learn they were born just a few years ago. Something about their personal history clearly does not match their apparent age. For this galaxy, astronomers do not yet have a fully settled explanation. One possibility involves an unusually violent, unusually early merger event, something that could have scrambled any initial rotational motion before the galaxy had a chance to properly organize itself, aging its internal structure far faster than its actual chronological age would suggest. Another possibility suggests current models may be missing something more fundamental about how rotation develops during the earlier stages of galaxy formation. If some galaxies can form directly into a settled, non-rotating state without passing through an earlier, more chaotic spinning phase, that would represent a real gap in current theoretical models, one that astronomers would need significantly revised assumptions to properly explain. Neither explanation is fully satisfying yet, and astronomers studying this galaxy have been careful to describe it as a genuine open puzzle rather than a solved mystery with a tidy answer already in hand. What makes the discovery matter beyond this single object is how well it fits, alongside everything else Webb had already found. Galaxies too big, too soon. Galaxies too calm, too soon. And now, a galaxy behaving too old, too soon. Each discovery on its own might be dismissed as an unusual outlier. Together, they were pointing towards something far stranger waiting in Webb's data. A brand new category of object that would soon become one of the telescope's single biggest and strangest ongoing mysteries. Scattered throughout Webb's deepest images, hiding among thousands of ordinary early galaxies, sat a population of objects unlike anything astronomers had previously catalogued. Small, compact, and strikingly red, these objects began appearing so frequently across so many different survey fields that astronomers eventually gave them an informal nickname: little red dots. The name fits exactly what they look like. In Webb's images, these objects appear as tiny, unresolved points of reddish light, nothing like the clearly structured spiral arms or glowing star-forming regions visible in typical galaxy images. No matter how closely astronomers zoomed in, little red dots refused to resolve into any recognizable shape at all, remaining stubbornly compact no matter how much detail Webb's powerful optics tried to extract from them. At first, some astronomers assumed these might simply be mature, aging galaxies, since older stellar populations naturally tend to glow redder than young, hot, newly formed stars. That explanation seemed reasonable at first glance, but it quickly ran into a problem. If these were genuine galaxies, filled with countless stars spread across a normal galactic-sized region, Webb's sharp optics should have been able to resolve at least some internal structure. Instead, little red dots stayed compact, packed into a region smaller than roughly 2% the width of the Milky Way, an almost impossibly tight space to cram an entire galaxy's worth of stars into. That combination, extreme compactness paired with surprising brightness, reminded some astronomers of a very different kind of object entirely. Not a galaxy built from countless individual stars, but a single, extremely dense, extremely energetic source, similar to the glowing material that surrounds a growing, supermassive black hole. As Webb continued surveying more of the sky, little red dots kept turning up again and again, far more frequently than any rare cosmic oddity should. Early estimates suggested somewhere between 3 and 4 out of every 100 galaxies observed during this early era of cosmic history contained one of these strange objects, a surprisingly high number for something nobody had ever previously catalogued before Webb began its mission. Their sheer abundance made them impossible to dismiss as a rare fluke. Whatever little red dots actually were, they represented a genuine, previously unknown population of objects hiding in plain sight throughout the early universe, invisible to every telescope that came before Webb. Astronomers now faced an entirely new question, separate from the oversized galaxies and the strangely calm disks and the impossibly still, non-rotating giant already troubling their models. What exactly were these small, red, endlessly common objects? And why had the early universe apparently produced so many of them, all clustered within the very same narrow window of cosmic history where nearly every other rule already seemed to be breaking down? Zoom in as far as Webb's optics allow, and a little red dot still refuses to become anything more than a single point of light. That single fact turned out to be the biggest clue of all. A true galaxy, even a compact one, is made of countless individual stars spread across some meaningful area of space. Point a powerful enough telescope at it, and eventually that spread starts to show, breaking into patches, clumps, or at least a soft blur wider than a single point. Little red dots never did that. No matter how much detail Webb tried to pull from them, they stayed stubbornly compact, squeezed into a region smaller than roughly 2% the width of the Milky Way. That measurement alone forced a hard question. If all that light really came from stars, how many stars would need to be crammed into a space that small to produce a glow this bright? Caitlin Casey, an astronomer at the University of Texas at Austin, ran into that exact wall while studying the little red dots. To explain their brightness using stars alone, the required density would be almost absurd. Stars packed shoulder to shoulder in numbers no known process in nature could realistically build. Nothing in galaxy formation, however violent or however fast, produces stars stacked that tightly together. Think of the difference between a stadium full of fans spread across open seating and that same crowd somehow squeezed into a single elevator, still breathing, still standing, packed edge to edge with no room left to move. A normal young galaxy looks like the stadium, thousands of stars scattered across a wide, breathing structure. A little red dot looked like the elevator, all that light and mass forced into an impossibly tight space. Astronomers spent months testing every explanation that fit inside the ordinary rulebook. Maybe these were simply older galaxies. Their light naturally shifted redder by aging stars. Maybe dust was clouding the picture, scattering light in a way that made objects look smaller than they really were. Each explanation got tested against the data, and each one kept coming up short. The size stayed too small. The brightness stayed too high. The math refused to balance. That left one option sitting quietly at the edge of the conversation. The kind of explanation astronomers usually reach for only after ruling out everything more familiar first. What if the light powering these objects was not coming from a crowd of stars at all? What if it was coming from something far smaller, far denser, and far more violent? A single source capable of outshining an entire young galaxy while staying invisibly compact. That kind of light source already had a name in astronomy, one usually reserved for the hungriest objects in the universe. Something that does not simply sit and glow, but feeds, tearing gas apart and heating it until it screams with light. Whatever these little red dots actually were, the numbers were pointing straight toward the most extreme object nature is known to build. A black hole on its own produces no light at all. Nothing escapes its grip once matter falls past a certain boundary, not even light itself. But feed a black hole and everything changes. Gas and dust spiraling toward it do not fall in quietly. They crash together, rub against each other, and heat up violently on the way down, forming a swirling disk that can glow brighter than every star in an entire galaxy combined. That glowing disk, called an accretion disk, is where the idea of a black hole star begins. Wrap a feeding supermassive black hole in a thick, dense cocoon of surrounding gas, and from the outside, the whole structure can start to resemble something else entirely, a single, yes, extremely bright, extremely compact point of light. Not a galaxy built from countless stars, but one hungry black hole disguised behind a curtain of glowing gas. Think of a bonfire wrapped inside a paper lantern. Stand close enough and the lantern glows as one smooth, steady source of light, hiding the chaotic flame twisting inside it. A black hole star works on a similar principle. The violent, messy feeding happening at the center gets smoothed out by the surrounding gas, emerging as a single bright glow that Webb's instruments simply cannot resolve into anything more detailed. This idea solved several puzzles at once. It explained why little red dots stayed so stubbornly compact no matter how closely Webb examined them. Since a feeding black hole and its immediate surroundings occupy a far smaller space than a galaxy full of stars. It also explained their surprising brightness, since accretion onto a supermassive black hole can outshine ordinary starlight by a wide margin, even while squeezed into a tiny volume of space. The colour also fit. Gas surrounding a growing black hole often carries dust, and dust tends to scatter blue light away while letting redder light pass through more easily. The same reason a sunset looks orange after sunlight travels through a thick layer of atmosphere. A black hole buried inside a dusty cocoon would naturally appear redder than a clean, direct view of the same object. Not every astronomer accepted this idea immediately. Confirming that an object is a black hole star, rather than an unusually compact, unusually red galaxy, requires careful evidence. Signs of extreme gas velocities near the object's center, specific patterns in its spectrum that only intense accretion can produce, details invisible in a single quick image. Teams across the world began combing through Webb's growing catalogue of little red dots, searching for one object clean enough, bright enough, and well measured enough to settle the debate directly. Somewhere in that search, hiding behind the gravity of a massive galaxy cluster, sat exactly the kind of object they needed, one that would eventually offer the clearest evidence yet that black hole stars are real. Deep inside the galaxy cluster Abell S10D63, astronomers were not originally hunting for little red dots at all. They were searching for something even rarer, signs of the very first generation of stars ever formed in the universe, giant balls of pure hydrogen and helium burning without any heavier elements mixed in, a population astronomers called Population 3 stars, never yet directly confirmed. While scanning that region, Webb caught something unexpected instead, an object designated Glimpse 65. At first glance, it looked like just another compact reddish point of light, one more entry in the growing catalogue of little red dots scattered throughout the early universe. What made this particular object different was how thoroughly it could be studied. The massive galaxy cluster sitting between Webb and this distant target acted like a natural magnifying glass, its enormous gravity bending and amplifying light from objects behind it, a real-world effect called gravitational lensing. That extra boost in brightness gave astronomers an unusually clear, detailed look at an object that would otherwise have been far too faint to study closely. With that clearer view, the team found several pieces of evidence lining up in exactly the pattern a black hole star should produce. The gas surrounding the object showed emission signatures inconsistent with a calm, orderly rotating disk of stars, the kind expected from an ordinary young galaxy. Instead, the gas behaved the way material caught in the extreme gravity near a feeding black hole is expected to behave, twisted, energized, and moving at speeds difficult to explain any other way. Researchers studying the object noted that earlier candidate little red dots had usually offered only one or two suggestive clues each, never quite enough evidence stacked together to feel fully conclusive. Glimpse WA775 was different. Multiple independent signatures, each one separately hinting at extreme black hole activity, all showed up together in a single object, all pointing in the same direction at once. That combination mattered enormously. A single unusual measurement can often be explained away by unlucky data or an overlooked alternative. Several unusual measurements, all consistent with each other, all pointing toward the same extreme explanation, are much harder to dismiss. None of this fully closed the case on every little red dot scattered across Webb's images. Astronomers remain careful about generalizing from one well-studied example to an entire population of thousands of similar objects. But Glimpse WA775 gave the black hole star theory its strongest single piece of supporting evidence yet, a real, gravitationally boosted, closely examined target instead of a distant, ambiguous smudge. If black hole stars really were hiding throughout the early universe, disguised as little red dots, one obvious question followed immediately. How many of them were actually out there? And what would their true numbers mean for how quickly the universe's very first monster black holes had managed to grow? Numbers can tell two very different stories depending on which ones you compare. On their own, little red dots sound rare, exotic, barely worth worrying about. Stack the right numbers side by side, and a much stranger picture emerges. Little red dots turned out to be anything but rare. Across Webb's deep survey fields, they showed up inside roughly 3 to 4 out of every 100 galaxies studied from the early universe, a surprisingly high number for something nobody had ever catalogued before Webb began its mission. That is closer to the frequency of a common street you might pass walking through any neighbourhood, not some rare landmark tucked away on the far edge of town. Compare that against a completely different number astronomers already had on hand. In the nearby present-day universe, roughly 10 out of every 100 galaxies show clear signs of an actively feeding central black hole, visible through familiar signatures astronomers have studied for decades. Push that same search back toward the first billion years of cosmic history, using those same familiar signatures, and the number collapses dramatically, dropping to a tiny fraction of 1%. Put those two numbers side by side, and something does not add up. If supermassive black holes really do form early and grow throughout cosmic history, as most models assume, there should be plenty of feeding black holes visible in the young universe, showing up through the same telltale signs astronomers use to spot them nearby. Instead, using the traditional method, they nearly vanish. Little red dots may be quietly solving that exact contradiction. If a meaningful fraction of these small, extremely common objects really are feeding black holes wrapped in thick cocoons of gas, then the missing black holes were never actually missing at all. They were hiding in plain sight, disguised behind a dusty curtain that made them look like something else entirely, invisible to searches built around older, more familiar black hole signatures. That reframing turns a shortage into an overabundance. Instead of a puzzling gap in the early universe's black hole population, astronomers may be staring at thousands of hidden black holes, common enough to explain 3 or 4 out of every 100 early galaxies, simply wearing a disguise nobody knew to look for until Webb arrived. If that explanation holds up under further study, it solves one mystery while opening a much bigger one immediately behind it. A universe filled with this many actively growing black holes, this early in its history, raises an obvious and uncomfortable question. How did so many supermassive black holes manage to reach enormous size so quickly, especially compared to the modest, still developing galaxies that were supposedly forming around them at the exact same time? In the nearby universe, black holes and galaxies grow together, locked in a careful partnership built over billions of years. Study any large, well-settled galaxy today, and its central black hole reliably weighs in at around 1,000th the total mass of all its stars combined. That ratio holds up so consistently across so many nearby galaxies that astronomers built entire theories around it, assuming black holes and their host galaxies grow in lockstep, each one shaping the other's development along the way. Webb shattered that tidy relationship almost immediately, studying small early galaxies from the first 1 to 2 billion years of cosmic history. Astronomers began finding central black holes 10 to 100 times more massive than that familiar ratio would predict. In some of the most extreme little red dot cases studied so far, the central black hole's mass came close to matching, or even exceeded, the entire stellar mass of its surrounding galaxy combined. Picture a toddler somehow carrying more body weight than both of their parents combined. That is roughly the scale of imbalance astronomers were finding between these early black holes and the modest galaxies supposedly hosting them. The partnership assumed to build up slowly over cosmic time looked instead like the black hole had already sprinted far ahead, growing enormous while its surrounding galaxy remained comparatively small and undeveloped. Astronomers studying this pattern gave these objects a specific label: overmassive black hole galaxies. The name itself captures the imbalance directly, black holes carrying far more relative weight than any nearby galaxy would ever display. Multiple independent research teams, studying different survey fields with different techniques, kept arriving at similar conclusions, making the pattern difficult to dismiss as one unlucky batch of measurements. Explaining how a black hole could grow this large, this quickly, forced astronomers to reconsider the physics of black hole feeding itself. Under normal assumptions, black holes cannot feed faster than a certain natural speed limit, called the Eddington limit, a balance point where the outward pressure of light produced by infalling material pushes back hard enough to slow further feeding. Cross that limit for too long, and the feeding process should choke itself off. Some researchers now suspect these early black holes spent extended periods feeding faster than that traditional limit allows, a state called super Eddington accretion, essentially outrunning their own safety brake for a stretch of cosmic time long enough to build enormous mass quickly. Others have proposed that some of these measurements themselves carry hidden errors, inflating black hole mass estimates in ways that could shrink the apparent gap once better techniques are developed. Neither explanation is fully settled yet. What remains clear is that something about the earliest chapter of black hole growth does not match the careful, synchronized partnership astronomers had assumed governed the relationship between black holes and galaxies for decades. And whatever process built these oversized black holes so quickly appeared to run out of steam surprisingly fast, based on an entirely separate clue hiding in exactly when little red dots stopped showing up at all. Every population of objects leaves a trace of when it existed, scattered across cosmic history like footprints along a trail. Follow those footprints for little red dots, and something strange happens. Plenty of them show up clearly during the first 600 million years or so after the Big Bang. Keep following that same trail forward in time, and the footprints start thinning out, then disappear almost entirely by the time the universe reaches roughly 2 billion years old. That drop-off caught astronomers off guard. If little red dots really were an early common stage of black hole growth, some trace of that population should linger as the universe continued aging, at least a smaller lingering fraction, the same way older versions of a common phenomenon usually stick around even after their peak has passed. Instead, little red dots seem to vanish almost completely, replaced by a universe that no longer produced, or no longer hid, objects quite like them. Some astronomers describe this vanishing act as one of the strangest parts of the entire mystery, arguably stranger than the objects themselves. A population common enough to appear in several % of early galaxies simply should not disappear this cleanly, this quickly, without leaving behind some kind of obvious evolutionary trail connecting it to whatever came next. A few possible explanations have emerged, though none of them have been fully confirmed yet. One idea suggests that little red dots do not disappear so much as transform, evolving into a different, more familiar type of galaxy once their central black hole slows its feeding pace and the surrounding cocoon of gas clears away, revealing an ordinary galaxy that had been hiding underneath the entire time. Under this idea, the little red dot phase would simply be an early, temporary stage, not a dead end. Another explanation points towards something more abrupt. What if the intense feeding process powering these objects simply cannot sustain itself for very long, burning through available gas quickly, or triggering violent feedback that blows the surrounding material away entirely, shutting down the glow that made these objects visible to Webb in the first place? Either explanation carries real weight, and astronomers have not yet settled firmly on one over the other. What both explanations share is a shift away from thinking of little red dots as a permanent, stable category of object, and toward thinking of them instead as a fast, temporary phase, a brief chapter in a much longer story about how the earliest black holes came to be. If that framing holds up, then every little red dot Webb has photographed represents a snapshot of something caught mid-transformation, glowing brightly for a short window of cosmic time before either settling down or burning out entirely. The exact mechanism behind that transformation remains one of the sharpest open questions in this entire field, and one particular theory about how these objects begin in the first place offered a surprising new angle on the puzzle. If little red dots really do burn out quickly, the next obvious question becomes how they got started so fast in the first place. One theory approaches that question not from the black hole itself, but from something far larger and far less visible surrounding it, the invisible scaffolding of dark matter that every galaxy forms inside. Every galaxy, including the Milky Way, sits nested inside a much larger invisible structure called a dark matter halo, an enormous cloud of matter that emits no light of its own but exerts gravity, shaping how gas collects and eventually forms stars within it. Most dark matter halos carry some amount of spin, inherited from the larger cosmic structure they originally condensed out of. That spin matters enormously for what happens next. A halo spinning at a typical rate tends to spread incoming gas out into a wide rotating disk before that gas can fully collapse, the same way water spreads outward when it swirls around a drain rather than dropping straight down the center. That spreading process is part of why ordinary galaxies form extended, structured shapes rather than collapsing entirely into one single dense point. Astrophysicists Fabio Pacucci and Avi Loeb proposed a different scenario for an unusual subset of dark matter halos, one spinning unusually slowly, a rare cosmic occurrence. Without enough spin to spread incoming gas outward into a wide disk, that gas could instead funnel almost straight down toward the center, piling up in an extremely dense, compact region rather than spreading out gradually. That kind of rapid, concentrated pileup could create ideal conditions for a black hole seed to form quickly and then feed aggressively on the dense surrounding material, exactly the kind of extreme, compact, rapidly growing object matching what little red dots appear to be. Under this theory, these objects are not some strange fluke violating the rules of galaxy formation. They are the natural, predictable result of an unusually rare starting condition, a slow spinning halo playing out through otherwise familiar physics. This theory does not necessarily compete directly with the black hole star idea. The two ideas address different parts of the same puzzle. One focused on how these compact, dense objects might have initially formed, and the other focused on what is physically happening inside them once they exist and begin feeding. Both could turn out to be pieces of the same larger picture. Even with this promising new angle, astronomers studying little red dots have been careful not to declare the mystery solved. Writing about the current state of research, one astrophysicist studying these objects described their nature as still an open question after several years of dedicated study, noting that nearly every new paper claiming to explain them uncovers fresh complications rather than a clean, final answer. And that pattern of solving one puzzle only to uncover another was about to repeat itself, this time involving not the birth of galaxies, but their surprisingly early deaths. Everything discussed so far involved galaxies growing too fast, too big, or too strange for their age. An entirely different kind of surprise involved galaxies that had already stopped growing altogether, shutting down while the rest of the universe around them was still bursting with new star formation. Astronomers call this process quenching. A galaxy that has quenched has effectively stopped building new stars, its gas either used up, blown away, or somehow prevented from collapsing into new stellar nurseries. Quenched galaxies are common today, filled mostly with older, redder stars rather than the bright blue newborns found in actively forming regions. Finding a quenched galaxy in the modern universe surprises nobody. Billions of years provide plenty of time for a galaxy to burn through its available gas. Finding one extremely early in cosmic history is a very different story. In research announced in 2025, a team studying Webb's data confirmed a galaxy designated Ruby's UDS QG-Z7, its light having travelled toward Earth for roughly 13 billion years. That places this galaxy at just 700 million years after the Big Bang, an age where most galaxies should still be young, actively forming, and far from finished. Instead, this galaxy had already built an enormous stellar mass, roughly 15 billion times the mass of our Sun packed into stars, and then stopped forming new ones entirely, all before the universe reached its first billion years of existence. One researcher involved in the discovery described the finding directly. This galaxy had formed that entire stellar population, and then halted star formation before the universe turned even 700 million years old. This was not an isolated case. A separate team confirmed another early quenched galaxy, this one containing roughly 100 billion solar masses in stars, built during an extraordinarily short burst lasting only around 200 million years, before shutting down almost as suddenly as it had started, existing at a point just 1.2 billion years after the Big Bang. Picture a sprinter who runs an entire marathon distance in the time it normally takes to finish a short warm-up lap, then immediately stops moving altogether. That is roughly the pace and abruptness astronomers were seeing in these galaxies, both in how quickly they built their mass and in how suddenly they stopped. Current models of galaxy formation generally assume quenching takes considerable time to unfold, gas gradually getting consumed, or a series of gentler feedback processes slowly starving a galaxy of new star-forming material. Finding fully quenched, already dead galaxies, this early challenges those assumptions directly, suggesting some process can shut a galaxy down far faster and far earlier than most models currently allow for. Massive galaxies too big, too soon. Calm disk galaxies too soon. Overmassive black holes too soon. And now, dead galaxies, already finished far too soon. Individually, each discovery might be explained away as an unusual outlier. Stacked together, this growing pile of surprises was starting to look like something much bigger than a handful of unrelated coincidences. Step back far enough from any single discovery, and a pattern starts to take shape. One far larger than any individual galaxy, black hole or little red dot on its own. Massive galaxies that grew too fast. Disk galaxies that stayed too calm. A giant galaxy that refuses to spin. Black holes that outweighed their own galaxies. And now, galaxies that lived fast and died shockingly young. Each discovery on its own might be written off as a strange exception. Together, they were starting to look like evidence of something the standard model of cosmology never predicted. That standard model, often called the lambda cold dark matter model, or lambda CDM for short, has served as the backbone of modern cosmology for decades. It describes how dark matter, dark energy, and ordinary matter interact to shape the large-scale structure of the universe, and it has successfully predicted an enormous range of observations, from the leftover glow of the Big Bang itself to the way galaxies cluster together across immense distances. None of Webb's discoveries have broken that model entirely. What they have done is expose a specific stretch of cosmic time, the first 1 to 2 billion years after the Big Bang, where the model's usual predictions and the actual observed universe increasingly disagree. Astronomers sometimes describe this gap using the phrase impossible early galaxy problem, a name capturing just how sharply these objects seem to defy expectations built from decades of careful modelling. Some researchers have gone further, suggesting the tension runs deep enough to hint at missing physics within the standard cosmological framework itself, something fundamental about how structure formed in the very earliest universe that current models simply are not capturing correctly. Others push back firmly against that framing, arguing that the existing model remains broadly successful and that these specific discoveries point toward gaps in our understanding of galaxy and star formation processes, not flaws in cosmology's foundational structure. This kind of disagreement is not unusual within science, and it is certainly not a sign that anything is broken beyond repair. Genuine scientific progress often looks exactly like this: a trusted model bumping up against a stubborn set of observations it cannot fully explain, forcing researchers to test, argue, and refine their understanding until a clearer picture emerges. The tension itself is doing real scientific work, narrowing down which explanations can survive contact with actual data and which cannot. What makes this particular moment feel different is simply the sheer volume and variety of surprises arriving together within just a few years, all clustered around the exact same narrow window of cosmic history. Oversized galaxies, overweight black holes, galaxies that refuse to spin, objects that vanish almost as quickly as they appeared. Every single one of these threads traces back to roughly the same brief, chaotic period right at the dawn of the universe's very first structures. Facing a pile of evidence this large, astronomers were left with two very different paths forward: either overhaul a model that has worked remarkably well for decades, or carefully adjust the pieces of the story surrounding it until the gap finally closes. Overhauling an entire cosmological framework is not a decision scientists make lightly, and most researchers studying these discoveries are not rushing toward that conclusion. Instead, the response taking shape across the field looks more like careful renovation than demolition, adjusting specific assumptions rather than tearing down the whole structure. One leading adjustment involves star formation efficiency, essentially how effectively a galaxy converts its available gas into actual stars. Older models generally assumed this process moves at a fairly modest, steady pace. If early galaxies were somehow far more efficient at this conversion than assumed, building stars faster and with less wasted gas, that alone could account for a meaningful chunk of the extra mass and brightness Webb keeps finding in galaxies that formed impossibly early. A second proposed adjustment involves something called the initial mass function, a technical name for the typical mix of small and large stars a galaxy produces when it forms a new generation. If early galaxies produced unusually large numbers of massive, extremely bright stars compared to smaller, dimmer ones, that alone could make a galaxy appear far more luminous and massive than its true underlying stellar population would otherwise suggest, without requiring any exotic new physics at all. A third adjustment targets the black hole side of the puzzle directly, focusing on that idea of super-Eddington accretion mentioned earlier, feeding faster than the traditional physical limit assumed possible. If early black holes really could sustain that kind of extreme feeding for meaningful stretches of time, it would help explain both their surprisingly large final masses and the intensely bright compact glow-powering objects like little red dots. A fourth line of research focuses on feedback itself, the various ways energy released by growing black holes and forming stars pushes back against surrounding gas. Powerful outflows from an actively feeding black hole, for instance, might explain why some early galaxies stopped forming stars so abruptly, effectively starving themselves by blasting away the very gas they needed to keep growing. None of these four explanations require abandoning the broader cosmological framework that has successfully described the universe for decades. Each one instead targets a more specific, more localized piece of the puzzle: the physics of star formation, the physics of black hole feeding, or the physics of feedback between the two. Adjusting any of these pieces changes how quickly and how dramatically a galaxy can grow, without requiring any fundamental change to how dark matter or dark energy shape the universe at the larger scales. This is how difficult scientific puzzles usually get solved, not through a single dramatic breakthrough, but through years of careful testing, competing explanations gradually rising or falling as new evidence arrives. Some of the four ideas above will likely survive closer scrutiny. Others may fade as better data rules them out. What remains certain is that the pace of new evidence arriving from Webb shows no signs of slowing down anytime soon. Records rarely last long around Webb, and that pattern itself has become part of the story. Within its very first year of full operation, the telescope had already confirmed a galaxy dating back to a redshift of 13.2. Within 2 years, that record fell to redshift 14.32. 6 candidate galaxies near the Big Dipper earned the nickname Universe Breakers within Webb's first several months of science operations. Little red dots, an entirely unknown category of object before Webb launched, turned up so frequently that astronomers needed a new name for them almost immediately. That pace is not simply a matter of luck. It reflects just how much of the early universe remained genuinely unexplored before Webb arrived. Earlier telescopes, however capable, generally could not gather enough infrared light from objects this faint and this distant to study them in real detail. Webb changed that almost overnight, opening up an entire, previously invisible chapter of cosmic history all at once, rather than gradually one discovery at a time. Astronomers involved in these surveys have compared the experience to exploring genuinely uncharted territory, arriving at each new deep field observation without a clear sense of what they might find. In several cases, teams originally pointed Webb at a target for one specific purpose, only to stumble across something entirely unexpected sitting nearby, the way Glimpse-Classington-75 turned up during a search focused on finding the universe's very first generation of stars. That combination, an enormous unexplored territory paired with an extremely capable new instrument, tends to produce exactly this kind of rapid-fire discovery. Each survey covers only a small patch of sky, yet keeps turning up objects that challenge existing assumptions, suggesting similar surprises are likely scattered throughout the much larger regions of sky Webb has not yet had time to examine closely. Scientists running these surveys have been candid about how quickly their own expectations kept shifting. Teams that set out expecting to confirm familiar, gradually built galaxies instead found themselves rewriting distance records, discovering entirely new categories of object, and documenting quenched galaxies existing far earlier than any model had predicted, all within roughly the same few years of observing time. If this pace continues, and current survey programs are already planned stretching years into the future, the population of confirmed early galaxies, confirmed little red dots, and confirmed overmassive black holes is almost certain to keep growing. Each new object adds another data point, another test for the competing theories currently trying to explain what Webb keeps finding. Whatever comes next, astronomers studying this field seem to agree on one thing without much disagreement at all. The current pace of surprising discoveries shows no sign of slowing, and the tools capable of pushing even further back into cosmic history are already being planned, built, and in some cases already pointed toward the sky. Every telescope eventually reaches its own limit, a point where distance, faintness, or resolution keeps it from seeing any further. Webb has not yet reached that limit for early galaxies, and astronomers already have specific plans for pushing it closer, one survey at a time. Ongoing and upcoming Webb programs continue targeting deeper, more sensitive observations of the same regions of sky where these strange early objects keep turning up. Longer exposure times allow astronomers to gather more of the extremely faint light arriving from the most distant candidates, the same strategy that confirmed the record-breaking redshift of 14.32 through nearly 10 hours of dedicated observation on a single target. Beyond Webb itself, an entirely new generation of ground-based telescopes is currently under construction, designed specifically to complement space-based observations like Webb's. The extremely large telescope currently being built in Chile will use a primary mirror measuring roughly 39 meters across, several times larger than Webb's own mirror. A larger mirror gathers more light, allowing astronomers to study fainter, more distant objects in far greater detail than currently possible, potentially confirming exact distances and internal properties for objects Webb can currently only detect as faint, ambiguous smudges. Future space missions are also being planned with these exact mysteries in mind. Proposed telescopes designed to study the earliest possible generation of stars and galaxies could eventually push observations even further back than Webb currently reaches, potentially catching light from redshifts beyond 20, corresponding to a universe barely 200 million years old, right at the very edge of when the first stars are believed to have ignited. Each of these future instruments carries the same basic promise Webb itself delivered when it first launched: access to a stretch of cosmic history simply invisible to whatever came before it. If Webb's own history offers any guide, that kind of leap in capability tends to produce exactly the kind of surprising, rule-breaking discoveries already piling up in its current data. Astronomers studying the little red dot population expect ongoing surveys to eventually settle several major open questions. Whether these objects really are dominated by black hole stars, whether the slow-spinning dark matter halo theory holds up under closer scrutiny, and why the population seems to vanish so abruptly once the universe passes roughly 2 billion years old. Similarly, the overmassive black hole puzzle and the mystery of galaxies quenching far earlier than expected both remain active areas of ongoing research, with new candidate objects and new competing explanations continuing to appear in scientific journals on what increasingly feels like a monthly basis. None of these open questions are likely to get fully resolved within the next few years. Big scientific puzzles rarely close that quickly, especially ones built on objects this faint, this distant, and this difficult to observe in detail. What does seem certain is that the next decade of observations spanning Webb, ground-based giants, and eventually new space telescopes will keep adding pressure to a very simple, very human question sitting underneath every single one of these discoveries. That question is simple to ask and difficult to answer. What does it actually mean that the universe built itself this fast? Every atom in your body heavier than hydrogen and helium was forged inside a star, then scattered across space when that star eventually died, later gathering together to help build planets, oceans, and eventually people capable of building telescopes and pointing them back toward the beginning of everything. Understanding how quickly the first galaxies, first black holes, and first generations of stars came together is not simply an abstract exercise in distant astronomy. It shapes the entire timeline behind how the raw ingredients for life eventually spread throughout the cosmos. A universe capable of building massive galaxies, active supermassive black holes, and complex chemical elements faster than anyone expected is potentially a universe that reached the conditions needed for life sooner than most models ever considered possible. That does not mean life itself appeared any earlier. Building a galaxy is not the same as building a habitable planet, and enormous amounts of additional chemistry and time still stand between an early galaxy full of young stars and anything resembling a living world. But every discovery pushing the timeline for complex structure formation earlier does shift the broader picture of when the universe first had the basic ingredients available for that longer story to eventually begin unfolding somewhere. There is also something quietly humbling buried inside all of this. For decades, scientists built careful, detailed models describing exactly how the universe's first structures should have formed, models supported by real physics, real mathematics, and real observational evidence gathered from earlier telescopes. Those models were not careless guesses. They represented the best possible understanding available at the time, built by careful people working with the best tools they had access to. Webb did not prove those decades of careful work wrong in some simple, dismissive sense. It revealed that the universe's earliest chapter contained more complexity, more speed, and more strangeness than any existing model had fully anticipated. A reminder that even our most carefully built scientific pictures remain provisional, always ready to be revised the moment a more powerful set of eyes gets pointed at the sky. That pattern, careful models meeting unexpected reality, is not unique to astronomy. It shows up throughout the history of science, again and again, whenever a new instrument or a new technique opens a door into territory nobody could examine closely before. Each time that happens, some fraction of the old picture survives intact, while another fraction gets quietly rewritten to match what the new evidence actually shows. Standing at exactly that kind of moment, astronomers studying Webb's early universe find themselves in an unusually rare position, watching a familiar picture of cosmic history get rewritten in close to real time, discovery by discovery, each one arriving faster than the last. Every single mystery covered so far traces back to the same brief, chaotic stretch of cosmic time, roughly the first 2 billion years after the Big Bang, a window representing barely 15% of the universe's current age, yet somehow producing nearly every major surprise Webb has delivered since it began operating. massive galaxies that grew far too fast for standard models to explain. Calm, orderly disk galaxies surviving an era once assumed to be dominated entirely by violent collisions. A giant galaxy that refuses to spin at all. An entirely new category of compact, mysterious object nicknamed little red dots, likely hiding supermassive black holes disguised behind cocoons of glowing gas. Black holes that appear to have outgrown their own host galaxies entirely. And massive galaxies that somehow lived an entire lifetime of star formation and then died, all before the universe reached its 2nd billionth birthday. Individually, any one of these discoveries might have been treated as a fascinating but isolated curiosity, an unusual object worth a single research paper, before fading into the background of ordinary astronomical catalogues. Stacked together, arriving within just a handful of years, they represent something considerably larger, a genuine, still unfolding challenge to how astronomers understand the opening chapter of cosmic history. Several competing explanations remain actively in play. Some researchers point toward more efficient early star formation. Others point toward exotic black hole feeding physics, capable of packing on mass faster than traditional limits typically allow. Still others suspect the answer lies partly hidden within the invisible scaffolding of dark matter itself, shaping which regions of the early universe collapsed quickly and which regions took their time. None of these competing ideas have been fully confirmed. None have been fully ruled out either. That is precisely the state science tends to sit in during its most active, most productive stretches, several serious explanations competing directly against real observational evidence, with new data arriving regularly to test and gradually narrow the field. Every survey Webb completes adds fresh evidence into that ongoing contest. Every confirmed distance record, every newly catalogued little red dot, every unexpectedly quiet or unexpectedly quenched early galaxy, adds one more data point that future theories will eventually need to explain cleanly, without leaving today's growing pile of strange exceptions unaccounted for. Somewhere in Webb's still growing archive of images, more surprises are almost certainly waiting, patient and unexamined, hidden inside faint smudges of light that nobody has carefully studied yet. Based on everything uncovered so far, whatever comes next from that archive will likely raise just as many new questions as it manages to answer. That has been the pattern since the very first strange dot turned up near the Big Dipper, and there is little reason to expect it will change anytime soon. Every mystery this telescope solves seems to reveal at least 2 more waiting patiently behind it, each one reaching a little further back, toward an origin story the universe is still in the process of revealing.